Thanks, Arthur. Yeah, as introduced already, this session 5, covers advanced exploration technologies, and we've got some interesting talks lined up, covering everything from geochemistry, geophysics, handheld scanners, and also innovative drilling techniques, and a few other items as well. So I'm going to introduce the first speaker now, who is Stefan Peters, who is the head of engineering geology in mining for the next project, and it's also working with a DMT GmbH & Co.kg. And so, Stefan, sorry.
Thank you. Hopefully you have had your coffee after lunch. And we can start with the project next. I would like to show you that's the Horizon 2020 European Union sponsored project. And okay. It runs 3 years. 1 year is over, and small first results I would like to show you. And this is a big project. 16 companies are working together, and 40% is industry, nearly 40 research, and 24% universities. One slide from DMT. So, what's that? Oh, that one? Sorry, I'm struggling around. Maybe it becomes better. Does it move automatically? It does. Okay. DMT is a company, 1,000 employees, working in former times with German hard coal mining industry, and now belongs to the TÜV Nord company. Let's go ahead with the next project. The main objective is developing innovative incentive exploration concepts and technologies, and to investigate to promote acceptance by the society. The technical related and economically related, and also environmental related, social related, and political related, all these topics had to be think about, and is based on 3 pillars: the mineral system modeling, the exploration method approach, and the data processing. And based on these 3 pillars, a lot of working groups are trying to extend the knowledge in different ways. That is a structure of the project with the working pillars, and from the things what we would like to investigate in special are 3 main things. This is unmanned aerial vehicles, geochemical exploration tools, and remote sensing tools. And therefore we have some objectives to update each of these tools. And the new geological lithochemical techniques for the exploration of high ore deposits enriched critical materials. The problem in Northern Europe is that 2/3 of Lapland is Natura 2000 area, and to make exploration there is a little bit more complicated, and to be more harmful to the environmental, and to use all the things you can do before you enter the area. You try to make investigations from a bigger distance, and try to get drilling targets more concrete, to have the lowest impact as possible for the further exploration. And therefore, looking for pathfinder like minerals or field spectrometers, and also from survey, from airborne or from satellite data, and integrate these data into 3D, 4D modeling, and definition of critical parameters which can be used for define special targets, and for mineral prospecting mapping. And with that, definition of zones of preferred targeting. That means predict the size of location, the targets for drilling. And that with more efficient, lower cost, and due to, if you see in Northern Europe, you have only small areas in the year to do something, so you can also save time by doing this from the air. So some examples. So EM drones were developed with two different techniques. One is to lay out an electric field on the surface and fly with the drone above it. Or we have at the end, hopefully, two drones, which one is the sensor, the other one is the emitter of the wave, to investigate in a small scale area the surface. So the transmitter loop system prototype 1 is ready, and some handheld portable receiver loop systems are also ready and tested and waiting for coming into the field. And prototype 2 is developed and is now under construction. For the novel exploration technology, vector magnetic field sensors in a small scale with high resolution are used to make investigations on the surface. Here's an area 1 kilometer to 1.6 kilometer. The same area is, you see the map are similar, only the vector is different. One is the x-axis and the other is the y-axis. That's from the magnetic field. And due to these data, you can model a 3D system under the surface, and after that you can extract theoretically ore body, and then you have more detailed drilling targets where you can go further with your next investigations. In general, you have the ore body, the red one, under the surface, and then it is covered by overburden. And then you have the vegetation, and in some areas also the snow above that. And due to detailed investigations, so geotechnical and geochemical investigations are from plants and all these materials, you can start find patterns which allowed you to interpret the potential deposit. Improvements of the software availability that are made by MINEX is by implementing new tools based on well-known methods equipped with data pre- and post-processing specially suited for the spatial geodata analysis and integration. And therefore, they enhance the ability of data mining. Yeah? Data mining, that is digging in a lot of data, geochemical data, geophysical data, structural data, and put these together and start producing maps. And the most advanced system is a self-organization map. You put the data in a black box and the map comes out, and hopefully all your functions are well organized, and the outcome is sensible. And therefore, we create the aim to predict maps for the investigation study areas and the different deposit types based on the development of data integration techniques for these self-organization maps and the ability technique of the artificial neutron network. If you do this, we have an example in Germany, very well-known country area, the Erzgebirge. And if you use these functions with these data which were available from this area, these are two maps, 100 kilometer long, 30 kilometers wide, this area, in this case, lithological controlled tin mineralization. And this is a prediction map where you can now use with expert knowledge to define more detailed drilling targets for the next exploration step. So, if you think this self-organization map is a glass bowl, you're looking in and seeing something, I would like to, show this one. What you see here is self-organization presentation, is it? Why didn't it stop? They are running the slides. Could you stop that? Hello? Ah, perfect. Yeah. You see here, data-driven approach. Okay. Time has come. Some problems with what I want to show is that you have a lot of knowledge in that picture. Okay. Maybe it did not work. In general, I want to, then I finish with this presentation. and if you have questions, you can download maybe the presentations after from the server, and then ask questions via email. In general, the next project is on the way, and we see, okay, here you see the locations where the tests were taking place, and of course we are always also, okay, so thanks. Also thinking at the environment by all our doing, and the summary is product for robust conceptual 3D models for selection target sites in the combination with Pathfinder allows to predict the location and the size of ore deposits in the depth. So, thank you. That was at the starting of the project, and these are the companies which were involved. Thank you.
Thanks very much, Stefan, and well battled with the technology challenges there. Obviously, if you have any questions, it'd be great to give them to Stefan via the app, or if we have time at the end of the session, hopefully then. Okay, so our next speaker is Chris Nind, who is the VP Business Development at Abitibi Geophysics, and his talk is on advances in induced polarization and borehole logging.
I'm scared of this. Okay, thank you to MINEX Europe for giving me the opportunity to talk to you. I'm a Canadian, and it's a pleasure to come to Sofia in Canada. Anything that's older than me is an antique, but not here. I want to talk to you today about induced polarization. And for the sake of time, I'm not going to talk to you about borehole logging, but if you have any questions, you can come and ask me. There's two common ways of ground geophysical electrical methods: induced polarization and electromagnetics. Induced polarization you would use for disseminated sulfides, alteration zones, porphyries, quartz veins. The EM induction method is more suitable for massive sulfides and graphite. Historically, conventional IP is a very well-known and well-used technique, but it has a limitation of about 100 meters depth for resolution and less than that under conductive overburden. So the question is, does this work? Should I press this button here? This one.
The other one.
The other one. This one.
Right hand side, yeah.
This one. Not the one that says forward. Okay. Gotcha. Induced polarization, the question our clients want is how do they want to see deeper with IP, but they don't want to lose the resolution. So how do we do that? Well, you can see deeper with IP by increasing the A spacing, or you can increase the N spacing. The sensitivity section, if you do just computer modeling, you'll see the issue with conventional IP. If you have A equals 100 meters, and A is the distance between the electrodes, is 100 meters. N is the distance between the two inner electrodes. So it's 6, in this case, N equals 6. The distance between those two inner electrodes is 600 meters. The distance between the two outer electrodes is 800 meters. And you can see that sensitivity section shows you can see about 100 meters down. Now, if you hold those two outside electrodes fixed and start moving the inner electrodes around, you can increase A spacing by moving them closer together. You'll increase your signal, but there's a limitation. You will also increase your noise and destroy your resolution. You can, with modern technology though, modern methods, we can move those two inner electrodes closer together. And by doing that, it's almost like squeezing a balloon. You see the sensitivity section, it just bulges outward and downward, and you get about 3 times the depth of penetration with the same resolution for A equals 25 meters. Now N equals 1 to 30. We haven't moved the outside electrodes at all. So if you have a body buried at 50 meters with conventional IP, 25 meter A spacing, N equals 1 to 6, you will see a body buried at 50 meters. You'll see the top, but not the bottom. And you will not see a body buried at 200 meters. It's beyond the range. If you increase your dipole spacing to A equals 100 meters, you will start to see that body buried at 200 meters. But if you increase your dipole spacing to 200 meters and trying to increase your signal, your noise is going to swamp you and you lose your response, so you won't be able to see it. However, if you reduce your A spacing to 25 meters and do N equals 1 to 30 with the modern technology and a system we call Eurasian, you'll see the body buried at 50 meters, the top and the bottom of it, and you will see the body buried at 200 meters. I'm going to show you 3 quick case histories of this. The first is the first Eurasian survey that we did. It was close to our head office in Val-d'Or, which happens to be sitting in the Abitibi region of Quebec, which is a very well-known mining camp in northern Quebec. And there's lots of induced polarization has been done. This particular survey I'm going to show you is in an area called the Cadillac Break. The area was covered with conventional IP, but there's a gap in the coverage where there's not a gap in the coverage, there's a gap in the chargeability, the very weak chargeability in one particular area. And they asked us to survey that area again with Eurasian IP to see what we can do. And Eurasian IP at 50 meters depth slice, you'll see that you just don't see anything. There's very thick overburden. This is why conventional IP can't see through this. It just can't see through the overburden. But with Eurasian now, you can see deeper in a 150 meter depth slice. You start to see a target coming out that conventional IP could not see. And it persists at 300 meter depth slice. So they drilled on this target, and they couldn't locate the drill in the optimal location because of water and swamps and things, so they actually drilled down dip. But they hit 150 meters of thick and altered copper-bearing granitic rock. So it's not enough to be a mine, but it was certainly a geophysical technical success. We have lots of technical successes, by the way. But we decided last year that we had this technology that we developed in Canada, and in Kazakhstan they have done a lot of conventional IP. They know how to do it extremely well. And we decided to bring over the Eurasian system to Kazakhstan to see if we can't see a little bit deeper in Kazakhstan. I'll show you 2 case histories from Kazakhstan. The first is Biryak case history. The landscape is very little vegetation. It's flat. Kazakhstan's got fairly conductive overburden in places. The client laid out the lines, and we don't recommend this type of layout at all because you get a lot of single line anomalies and you just don't know whether the targets are under the lines or off the lines. But this is the way they wanted the survey done. I'll show you two results from line 1 and line 2. Line 2 is about a kilometer north of line 1. In the top, line 1, in the top of this slide, you'll see what an IP pseudo section looks like. It's very difficult to see anything in that, so you have to interpret it, you have to invert it. But when you do the inversion, there are two targets that pop out. They're shallow, they're about 50 meters down, and they're in zones of high resistivity and high chargeability. So we have a little algorithm that's a qualitative algorithm. It doesn't have any quantitative meaning. It's a qualitative algorithm, but it enhances these particular types of targets with high resistivity, high chargeability. And somebody in their wisdom in the past called it the gold index, which is a terrible name for it, but it shows high resistivity and high chargeability zones would be amenable to hosting disseminated sulfides and quartz veining or alteration zones. Line 2 shows you quite a different story. Line 2, there's a couple of targets on the left-hand side of this slide. Yeah, left-hand side of the slide you're looking at. These are about 300 meters down, and they are in zones of low resistivity and high chargeability. And in that case, we have another type of algorithm which we work through. We take the chargeability and we divide by the square root of resistivity. It's called a metal factor, and it highlights regions of low resistivity and high chargeability that are amenable to hosting disseminated sulfides in shear or faulted environments. So depending on what the geology is in your area, this particular line 2, these types of targets would be similar to the target that I showed you in Canada in Cadillac Break, where you have low resistivity and high chargeability. But you need to bring in the geology to choose which targets you want to follow up on. Kloskovsk project is another project in Kazakhstan. And in this case, there was a prior survey done. These are the purple lines, or the red lines, sorry, that was done in conventional IP in 2016, and we redid it with Eurasian last year. The mineralization in this area is to be found in altered rocks. So you would expect the anomalies of interest to be high resistivity and high chargeability. So you would look at the gold index. So in this case, line 26, I'll show you this. You'll see on the right-hand side, well, on the left-hand side, there's two targets there that are in zones of low resistivity and high chargeability. And the target on the right is high resistivity and high chargeability. And given that the information that we've got on the geology, we would prioritize this right-hand target, the K03 target, as our primary target in this line. We can stack these lines are 600 meters apart, which is still quite far apart. We would prefer it to be 200 meters apart. But you can start to see on line 26, which is the third line up, towards the right of that line, you see the chargeability high and the resistivity high, which is in blue and white there. So that's the target. At 100-meter depth slice, it doesn't really show up too much. At 300-meter depth slice, you start to see the target. It's about 300 meters down. And at 500 meters, it's beginning to disappear. So that's the results of 2D IP. what we can do with 2D IP, and we can take the next step and go to more expensive, much more expensive 3D IP arrays, which are, give you better depth, better resolution, but also for a higher price. This is a high power 3D. You lay out a bunch of cables, and you basically take 30,000 dipoles measurements per setup. So there's a lot of data to work your way through. We also have a distributed array, which you lay out a bunch of receivers over the blue dots. They're completely independent. They're all GPS controlled, synced with GPS. They're not joined together at all. They're not linked with any wire, but you lay them out over an area, and then you inject current in all of those locations with triangles or surface injections, and the strings of purple dots are borehole injections. So you can do that. Once again, it's more expensive, but it's another way of getting depth of resolution, depth with IP. But I want to thank Alexander Minerals and Viriak and Caravan Capital for releasing the Eurasian data sets, and to MINEX Europe for the opportunity to show you this. Thank you.
Great. Thanks very much. Very interesting stuff, and obviously very applicable where these deeper buried targets are located just away from easier exploited areas. That's often the case these days. So our next talk is by Alexander Mikhailov, who's director at Mineral Exploration Network.
Good afternoon, ladies and gentlemen. I would like to present some innovative technologies which we are using to carry out really intensive exploration in big areas. Our company, Mineral Exploration Network, formed in 2009. Our main business is early stage exploration, and we are based in Wales, United Kingdom. If you think that I am speaking with Welsh accent, it's wrong. I'm speaking with Russian accent. Main strategy of our company, first of all, informative target selection. You obviously should not prospect area where you don't hope to find something. And as soon as you select that area, you should carry intensive exploration, and to carry intensive exploration on as many targets as you can. So we strongly believe that successful exploration depends on number of samples you are taking. In fact, quality of your exploration program, prospecting program, it's number of samples which you can collect and analyze. But how many samples you need to take to discover mine? Practical experience summarized in Hard Rock Miners Handbook published in Canada says that you need to prospect about 4,000 square kilometers to delineate about 80 kilometers worth of drilling, and just after drilling this 80 kilometers you can find a mine. So if we'll turn it to number of samples, it means that in fact you need to pick up and analyze more than 100,000 samples. And if you are talking about Europe, someone may say that Europe has a lot of mining history, a lot of good exploration data. We can come, select, pinpoint target, drill, and get to resources. Of course, you can tell it to your investors, but we'll see what the result will be. There is one good example from Spain. This map was published more than 100 years ago, in 1887. Modern map differ just by fact that it was drawn on computer. All structures, all alteration hollows, all the same. Last systematic exploration was done in '82. They did very systematic trenching along the known structures. And by 2014, we carried out detailed geochemical survey. And the result is obvious. The thing is that in 1982, geologists did not have that technical ability which we have now. They could not analyze such amount of samples which we can analyze now. But before we discovered this one is, by the way, a new discovery and with proven high-grade tungsten. And to come to this discovery, first of all, we prospected more than 2,000 square kilometers. Then we delineated more interesting targets. This target took us about more than 80,000 samples to pick up and analyze. Result, very clear and understandable. Very clear and understandable picture when you can see hidden intrusion, blind intrusion, you can see alteration front, and it easily leading you to your drill targets. But we are a small company, we have limited budget. It's very difficult to find money for assaying so huge amount of samples. So solution is very simple, portable XRF. At this moment, I'm usually reading commercial advertisements about Olympic 1 to Olympic Delta, but Todd will be giving presentations shortly, and he will do it better than me. So, but portable XRF, it's not innovation. It's on market for a long time. I'm just wondering, why not yet every prospecting team have portable XRF in the field? It's giving great advantage. So portable XRF allow us to take up to 1,200 samples and analyze the samples the same day in the field without any sample preparation. So, but what does it mean, analyze 1,200 samples? It means that you need to keep in base camp 2 or 3 field geologists who will be putting samples on the XRF, pressing button, waiting for 30 seconds, and so on. But that gives, those 2 or 3 geologists can go in field and collect samples, so it's not cost effective. So solution could be very simple. Effective, it's child labor. I understand that it may be not legal in some countries. So then we advise to use automated CNC platform. With this one, you can analyze much more. You can analyze up to 2,500 samples per day. It can work 24 hours and never make mistakes. It just do what you need. And cost of this platform is less than, let's say, two months salary for exploration geologists. But the only problem was for us that our primary target is gold, and XRF does not analyze gold. So sending samples, can you imagine 100,000 samples to be sent, let's say, to LS? It's more than 2 million. We never had that money. So we were forced to develop a patent and introduce a new geochemical method, which we call multi-element fine fraction analysis. It's very simple. We are taking fine fraction from samples, putting on a glass palette, and putting it laser ablation, and analyzing it with mass spectrometer. Sample preparation is very simple. It could be organized anywhere in the field where you have dry place and clean running water. Sample preparation, very simple. You just take glass with water, put sample there, mix it with water, wait a bit when heavy fraction settles, then pour muddy water in another glass and let it settle and dry. So we are taking, by this way, we are avoiding nugget effect. We are avoiding that free particles of gold in sample. We are avoiding heavy minerals containing gold, and we are analyzing gold which is associated with fine fraction. Because we are avoiding nugget effect, our samples could be small. On the left, you can see our field sample. It's just 30 or 50 grams. After processing, it's just 3 or 5 grams. And these 2 boxes at 800 samples just arrived in the lab. It means that you can walk anywhere in the world where you have clean water, dry tent, and you can send it, not that huge pellets, just 2 small boxes, 800 samples. But of course, the most interesting part, how reliable is analytical method. Here we had run several test walks in different landscape conditions, and here you can see that results of MEFA, shown in orange, they're compatible and have quite often has better resolution than traditional analytical methods. But this one is a comparison of analytical results. This one a bit more interesting. This one is sampling control. So we were running exploration for our client, and we asked client to run control profile. That day, our geologist alone took 196 samples. Our way, small sample, just under organic layer. Client sent team, 1 geologist and 2 helpers. They took just 86 samples, and our geologist was waiting for them for a couple hours when they will finish this work. So MEFA, it's not just analytical method, it's system when you can take more samples, quicker, cheaper, and cover better, bigger area. So for us, it was obvious benefit. We was able to delineate about 25 kilometers of gold anomalies just on one of our projects. And now we definitely can say that we have discovered a large multi-commodity gold and tungsten target. So multi-element fine fraction analysis has high production rate, very cost effective, minimum sample preparation, and it's environmentally friendly. We are not using any chemicals, we are just using pure water. Even any clean stream will be good. But we discovered anomalies. What next? We need to find source. Now we need to take hard rock samples. Unfortunately, MEFA does not work for hard rock samples. MEFA designed particular for soil and stream sediment samples. But then we decided that in MEFA we are avoiding nugget effect. Maybe we can use nugget effect to our advantage, especially that we already have XRF. Why we do not do just a lot of measurements on one sample? So, and we call it nugget effect gold assessment. Yes, it takes time, because from our experience, you need to take at least 100 measurements, but you are getting results right in field. In fact, the idea is very simple. When you put XRF in, gold never distributed in samples equally. So there will be always grain with gold or minerals containing gold. And if you did not pulverize sample, it always will be place where you put your XRF and you will have a high reading. So on table you can see how a sample with about 7 grams per ton looks like. We ran many tests and we came to conclusions that if we are doing about 100 measurements per samples, we easily can split samples to find samples with grade more than 0.2, 0.3 grams per ton. If we are doing 400 measurements, then we definitely can see gold starting from 0.1. But obviously 400 measurements, it's not practical because it's taking too much time. But 100 samples, we are now working with latest model of Olympus Vanta, and we can do one measurement, 100 measurement sample in 10 minutes. It means that a day you easily can do about 80 or 100 samples. How many hard rock samples you are taking in field exploration on early stages? It's more than enough. It's even compatible with drilling rate of small RC drill rig, and you will have results next day. I would like to say one time more, it's not gold assay, it's gold assessment. But you will be able to see your gold intersection immediately, and you will be able to reduce number of samples which you are sending to external lab. And of course, you don't need to use manual labor. You can use the same CNC platform to automate measurements. So NEFA nugget effect, the gold assessment is easy to implement if you already have XRF. Any XRF model will be working, but Vanta is faster. very simple sample preparation or absent of sample preparation, because you need to carry measurements on crushed material. So we recommend it should be about -2 millimeters. You don't need pulverize it. It's quick, and it's helped to reduce number of samples which you are sending to external lab. And next step of development was that if we have XRF, if we have CNC router, why will not go further? So now we are working and prototype already in test mode. We developed automated system for call logging, photo documentation, and XRF analysis. It will be on the market starting somewhere in September. Now you can come to our booth and to look on online simulator and just tell us what you think about it. So, being a small company, we were forced to introduce cost-effective methods, and we will be happy if you will find it interesting and will decide to use it in your exploration. Thank you.
Thanks, Alexander. If there are questions, we'll invite them at the end. Certainly some interesting examples of modern grade analysis, and could be potentially very useful. Great, thanks. Okay, so our next talk is by Jane Shaw, who's a principal consultant at ERM. So, Jane.
Hi there. Oh, sorry. Hi there. Thank you for the opportunity again, and welcome to everybody here. So I'm going to be talking about combining catchment modelling with geochemical assessment to put the two together to come up with a mineral an exploration targeting tool. It's something slightly outside of ERM's sphere of expertise, but it marries two things we've been doing in isolation for years now. Let's see if I can. So thank you. Okay, so ERM's philosophy with water assessments and mining assessments and so on is a holistic catchment scale approach. We like to take into account all of the factors that may affect or impact your project before sort of zooming into the fine scale details of where the important things are. So, and we apply this across the mine life cycle. So you can see on the figure at the top there, we start at targeting and we run through all the way through to closure. And we apply a mixture of the same tools. Some of our tools sort of grow exponentially as we go, and some of them sort of come in and start and finish, as you can see in the sort of list of tools underneath it. And the figure below sort of describes how it's not just your impact on the environment, it's the environment's impact on you, as we've seen. And that environment can be social, it can be stakeholders, it can be climate change, it can be financial, it can be anything. So we like to look at all of it and put your site in context. So I'm not going to go through all of those at the moment. I'm really just going to focus on that targeting and exploration aspect for the CSET. So what is it? It combines two technologies that have been around for decades. So groundwater modelling has been around for a long time, and the geochemical analysis has been around since the late 70s, 80s, but nobody's really put them together the way that we have. So it's something we've designed and something we've tested out, and we feel it really works. So the groundwater model is, we start at a catchment scale, so we don't need a lot of drilling, we don't need a lot of existing data. We can literally do it with a DEM, a digital elevation model, and maybe a bit of spring data to give us water elevations and so on and so forth. And then we take groundwater geochemistry, so it's not sediments, it's not surface water, it's groundwater from springs or wells or boreholes or old. So this is kind of where the idea came, is that a lot of environmental impact assessments carry out baseline water quality sampling, and usually nobody's using that except for the EIA perhaps, and all of this data is really useful for this technique. because we need very simple analyses. We just need the majors and a few of the trace elements. It's not costly analysis. It doesn't matter whether it was taken 20 years ago or 2 days ago, because the geochemistry doesn't really change once you've got the results. So we then process that. We're not looking at the raw geochemistry, we're looking at the mineral phases that are in thermodynamic equilibrium or disequilibrium with this water chemistry. And we process it through Freaksea, which is freely available. And it comes up with a suite of 600 to 900 mineral phases, which is obviously too many, but geologically there is a relationship between the element, the raw element in the water, and the mineral, and a mineral set of mineral phases. So when we've identified the mineral phases that are in geological association with the raw geochemical results, we say this is our mineral suite for this sample. And that mineral suite tells us a lot more about the rocks that the water has flown through. So you can see on the figure here, that's basically the theory is water falls as rainfall with a certain chemistry, and as it goes through the ground, it interacts with all of the minerals it comes into contact with, and at different rates. So the kinetics for mineral reactions are different. Some of them are very slow, some of them are very quick. And then you take a sample at the end, and you're left with a signature of the whole life history of that water sample. So the mineral phase assemblage for each sample tells us a story about that history of the groundwater sample. What have I got? Yes, okay, so two versions. Either you've got the data from old sources, government sources, EIAs, you've been out and collected it in your exploration program, in which case it's a data set, or you haven't got any data, you've got a big area that you're interested in applying this technique. Where do you start to sample? So we can create the groundwater model and say, if you want to sample these areas, or if you want to cover the whole area in a sort of a broad-spaced sampling program, this is where you should take your samples. So that's a sampling C-set. So this is so then we've got this sample with its anomalous result, or not anomalous if you're trying to sort of define areas not to explore. And then we put the location into the groundwater model, and we do basically backward particle track analysis to say this water molecule has travelled in this direction through its life cycle. So somewhere along that groundwater contour, or not contour, that groundwater flow path, is where all of the minerals that we're now seeing, the mineral phases that we're now seeing, are sitting. So you can see, you can quickly identify groundwater subcatchments that are either anomalous, weakly anomalous, strongly anomalous, non-anomalous, and you can also identify gaps. So these are the areas I have covered in my sampling program, and these are the areas that are missing still. So you can sort of start with a broadly spaced one, and you can infill in areas where you're getting nice results. And as I said, the key thing about this catchment model is that it's so relatively easy to set up in terms of, groundwater models, the mod flow type are extremely expensive to set up, whereas this one requires limited data. It can be done using mostly open source information or local information if you've got it, and it's really robust. We've done case studies and examples where we didn't use any client data, and we recreated the conditions they were seeing at their sites. So when would you use it? Grassroots exploration, as I've just described. You can generate targets, or you can rank targets. So this sits really nicely in terms of, I've got geological, geophysical, geochemical targets, and I want to sort of have an extra tool to rank them into testing targets. It works in areas where you've got known mineralisation. So there are certain mineral phases that can identify whether you've had anthropogenic influence on your sample. So we can see if the sample has come through, say, a tailings, or it's got some sort of anthropogenic influence on it, and we can see whether it's a pure sulfide that's sort of buried and blind. And I should say, of course, that because this is testing groundwater, there doesn't need to be any surface expression of your mineralisation. We've used it, I've got some case studies coming up. We've used it in several examples where they were covered by hundreds of metres of post-mineralisation cover, and and people sometimes ask, you know, what if the structures don't come to the surface? But that's why we set out our catchment model at the scale that is appropriate, because eventually the water will come to the surface. And we're not talking about decades or years or months, we're talking about, you know, thousands of years potentially, because the kinetics of the reactions that we're looking at are slow enough that works. So obviously you can do some sort of due diligence. Do you want to sort of assess an area quickly before you surrender it? Or if you can get access to data, you know, legally, you can do it on areas where you don't hold tenure. So if there's open source data, you can do it on those areas. So the case studies, if I can get this go on. We've got 3 case studies to show you. Conceptually, the ideal environment to do this is temperate climate, hilly terrain, because you've got a nice digital elevation model to create your groundwater model, and you've got some nice rain to make the groundwater flow at a reasonable pace. So this was the first one we did, and we covered a large area. I can't read what that says there, 1,500 square K. We had a really nice selection of known buried mineralisation, worked mineralisation, surface mineralisation, and large non-mineralised areas. And so it was a really nice case study. And what you can see on the figure, on the various figures, I've got the examples of numbered there, so SI anomalies. When I say SI, I mean saturation indices, so these are the mineral phase anomalies. Downgrade gradient of known mines or surface mineralisation from the main one is in the middle, really. It's where we were looking for a signature of an existing known deposit that's buried. And what you can see in the little stars, let me see if I can make this work. Yeah, okay, so the little stars are the sampling points, and these are all springs, and the surface expression of the deposit is here, and I don't want to burn anybody's eyes out, but the figure in the bottom is a 3D image of that deposit, and it's buried. And you can see the closest sample there is in red, so that's our very anomalous, our strong anomaly. And as you go further down the groundwater flow path, further away from the deposit, you start to get a weak anomaly, and on either side, we've got no to very weak anomalies. So it really identified for us that we were seeing this deposit. And it's not just the fact that, so when I say a strong anomaly, I mean that the mineral phase association in that sample really reflected what you're seeing in the deposit. So it's not, we went from sort of altered, weathered sulfides in the further ones to chalcopyrite and pure primary sulfide minerals in the closer one. So that was our first example, and a very nice one. So moving on to other climates. This is semi-arid and mountainous, and this is all open source data. Sorry, not open source data. This is the company's database from years of environmental baseline assessments and assessments of where to put their tailings, assessments of you know, the influences that they're going to have on local farmers, water bores, and so on and so forth. So big data set that they weren't really doing anything with. And you've got surface water and groundwater here, and this is one of the instances where surface water worked really well in a couple of cases, because you've got streams here that are perennial, streams here that are seasonal. They only run, they run all year round. I get this right. They run all year round, and yet it's very arid for periods of years. So they are groundwater fed, and in those samples we were seeing some nice groundwater results. And again, so you can see there's a big range of topography change. That's what the figure at the bottom is there. And we are seeing evidence of indications of the existing mineralisation that's obviously well structured, well studied, and also other areas of interest that the company is now looking at chasing up. So they'd had other reasons to like these particular areas, and our results were interesting to them, because like, okay, so you're finding the anomalies in this area, we really like this area, and it gives us another reason to go back and have a look at it. So that's the second example, and the last case study. There we go. It's kind of like our worst nightmare when somebody came to us and said, oh, do you want to do it here? And it's completely flat and it's really arid. And we're like, okay, let's see if it works. So these are open source data. So this is a government database of water supply bores. And we got them from the government and we processed probably, I don't know, 1,500 results. And the QA/QC whittled them down to something like 70 results, I think it was, 47 sites and 70 odd results from different dates. And so this was an interesting one in that what you can see in the contours is the groundwater contours, and the sort of big circle here is dewatering from the existing mine. And don't worry that the flow paths don't match the contours, they were two separate runs. And the groundwater is very slow flowing here. So each of those tails is the groundwater flow path from a sample site for 4,000 years. And we didn't want to go further than that because obviously the climate is slightly different then. So, or rather, the climate is different enough that we're not sure that the groundwater model is valid. So we were looking, all of these water supply bores were, they were sampling the cover. None of them went into the basement, which is what we were interested in. So another thing we were thinking, okay, is we're not really interested in the cover rocks because they've got no mineralisation in them. But we could tell from the groundwater model which of those flow paths actually came out of the basement into the cover. And so that narrowed down our number of our interesting samples as well. So in this one, our sort of technical success is this. So, well, these two samples are in the just above the tailings, so that's great because they're anomalous. And this one is 7 kilometres away, and although it's a weak signature of the mineralisation, it is a signature of the mineralisation. So we're able to say that the technique works in this area. Not only are we seeing the signs of the mineralisation, but we're seeing quite far away, and we're able to get a signature from basement in cover rocks. So we've identified a couple of other interesting areas which haven't been drilled yet, but the company involved was dead keen when we showed them this result, because again, this was a couple of areas that they were interested in. So perfect timing. That is actually the last slide. So thanks very much.
Great, thanks very much.
Добър ден. Hello everybody.
Hello, good
My
afternoon.
name is Romov. I have a big dilemma. Shall I speak English or Bulgarian? English? Yes? Or no? Okay. So, I'm lecturer in the University of Mining and Geology, and also I'm part of the team running a small company which provide directional drilling services. So in my presentation, I have put both logo, university and the company. So the presentation is related to modern development, which is very important for the exploration business. And it summarizes my knowledge and experience with the university and the company. So this is the agenda of my presentation. What is directional drilling? Actually, it's a technology which uses special tools and technology to steer the borehole. And here's an example of an extensive directional drilling program. You can see how many holes are drilled to reach the ore body and to make a penetration. So talking about directional drilling, there are two main approaches. The first one is borehole navigation, which means that we use this special technology to follow a predefined path and reach the ore body, while the second one approach is multilateral borehole. So we use one main mother borehole and then make a couple of branches. A couple of examples about the application of directional drilling is when we drill a borehole and we miss the target, as shown in the example. So what we can do in this case, we can cut a branch somewhere in the middle section of the borehole, and then deviate the borehole and reach the ore body. It's expensive. Another example about application of directional drilling in smooth or lateral drilling, when we have extensive program to explore and license, then we may have a couple of pilot boreholes, and then from those boreholes we can cut branches. So at the end we have a bunch of boreholes which reach the target, and then the picture is like this. Another application of directional drilling is when we have targets which are near each other, so we can drill another borehole and then branch off, reaching different targets. Another application is related to geotechnical conditions which are very difficult to drill the upper part or the upper section. Then we can drill another borehole, case it, and then make a couple of branches reaching different parts of the ore body. So I'll go back to the first example in the presentation about a borehole which is missing the target. What we could do, instead of doubling the borehole, we can control the borehole during drilling and make one or two or more deviation in order to reach the ore body. Couple of other applications of the directional drilling, when we have problems with the drill string, when we do rise boring, then we need to reach a target in the mine, and difficult to assess zones where the environmental issues are restricting the drill sites. And talking about deviation, borehole deviation, it is important to create a side force in the drill bit. There are two main principles to create the side force. The one is when we push the bit, create a side force, and the second principle is when we tilt the bit. It's shown on those two pictures. The main tools used nowadays in directional drillings are the wedges. It's quite old technology. The steerable boreholes, steerable core barrels, bottom hole motors, and wedging tools. The wedges, there are two main design, the permanent wedges and the retrievable wedges. The application is made for short jobs when we make one or two deviation. Recently, a new design of a wedge appeared in the market. It's so-called zero-tip wedge, and you can see in this slide comparison between the conventional and zero-tip wedge, how much time we save in the conventional and the zero-tip wedge. As to the bottom hole motors, in drilling we use two kinds of motors, the positive displacement motors and the turbines. In the diamond drilling, the application is mainly related to positive displacement motor. And the operation characteristic of this type motors, both type motors, is that they heavily depend on the hydraulic. I mean flow rate and pressure losses in the system. Here is shown a typical positive displacement motor with its component. Something that is important, it's operational characteristic. You can see the flow rate, the speed, the RPM, and the torque of the bottom hole motor. It required quite high volume or quite high flow rate to get the operation in a proper operation window. The steerable core barrels, there are a couple of different designs, but they can be mechanically or hydraulically operated. Both type of steerable core barrels work on the push the bit, tilt the bit, or retrievable system for getting core from the ore body. The steerable core barrels, this picture shows maybe one very old design, which was patented in 1968, I think, in Bulgaria, while now the most popular system used in the industry is the Davy drill. On the next slide, I'll show you how the design of the Davy drill looks like. It's hydraulically operated tool. It uses the tilt-the-bit principle of operation, and its application is for a long section of deviation of the borehole. Some of the main characteristics of the tool is the length, about over 5 meters, the diameter of the core, it's 31.5 millimeters. The intensity of the borehole deviation, or the so-called dock-length, is between 0.1 and 0.5 degrees per meter. The next type of tools used in direction drilling is the wedging tools. They use mainly the push-the-bit principle, application for short cuts and making series of cuts in order to steer the borehole towards the target. Here's how they work. Actually, we have a sliding pad and wedges. When we apply axial force, then the slide pad applies force towards the borehole wall, and on the bit we get the side force which deviates the borehole. Some specification of the wedging tool: the length, the diameter, the hole size, the weight, and the dock-length CVT, which is between 0.2 and 1 degree per meter, which means that the tool is very aggressive and we can get a very, very strong deviation of the borehole, which means that we have to be very careful applying this tool for steering the borehole. In the next part of the presentation, I'll present a couple of case histories related to projects done with the tools. The first one is Jurong Island. It was a project which is related with geotechnical investigation of tunnel. Which was supposed to, for storage of oil for refinery, used for refinery. And then the drilling program consisted of 6 boreholes, which were started with a deviation of 30 degrees, and then deviating the boreholes and horizontal section with length between 4 and 500 meters, 6 boreholes with total length of 2,400 meters. The next example is about the project run in Hong Kong. It was a tunnel, Eagle-Ness Tunnel. The drilling program included 2 boreholes from both sides of the tunnel, and then the safety envelope was with a diameter of 16 meters, and one of the borehole, this one, was with a record length for a horizontal borehole, 1,150 meters length. The next example is from Peru. It's a Santander project. The drilling program includes 3 boreholes with 3 to 5 branches. They are shown on this picture. For all the branches, 65 cuts were made, 189 meters directional drilling, and totally were saved for one of the borehole 900 meters, for the other 2,120 meters. And the last example is from Canada, Copper Cliff project. The project was related with cement squeezing. Actually, 2 groups of boreholes were drilled, vertical boreholes. For first the group, this picture showed the schematic. So the goal was to drill strictly vertical boreholes, and this is one of the boreholes. We made actually 3 deviations, here, here, and here, in order to get the target in 336 meters. The limits, the safety limits, or 0.9 meters. That's all.
Thanks. Thank you very much, Mr. Terry. It's very interesting and some good insights into the latest drilling technologies. And of course, if there's any questions from the audience, let's either go via the app or after the session. So thanks very much. Now, who's next? We'll wait and see. Yes. Oh. Okay, you've been bumped down the list again, Todd. And now, I think this is from the next session, Hanno. Is there one from Todd Houlihan? I think he was next on the list. Oh, is it? Okay. It should be either Todd or Nijaz. Yeah, or is there one under Olympus? Oh, come and have a look. I think it's for a next session. There should be one for Olympus. Yeah, Todd. Take that one out. Slight technical hitch, but we'll be there shortly, I'm sure. Okay, yes, right, okay, we're ready. This talk is by Nijaz from GEOPS Drilling Services, who's the country manager there, so you can just take it away, thanks.
Thank you, and congrats to the organizers of the event. It's a productive gathering, and it's my pleasure to be here today and to speak about some modern challenges in the drilling business. Could be kind of like a continuation of the speech of the professor. So to begin with, our company, full name GEOPS Balkan Drilling Services, was established back in 2004 with a focus on surface and underground drilling services in mining, exploration, and geological industry. And over the years, the company managed to respond adequately to the requirements and requests of the customers, placing itself as a reliable and trustworthy drilling contractor to many investors here in the Balkans, around Europe, North Africa, and as you can see, this is the network of our location, so to say. The headquarters is here in Bulgaria, with a number of offices and field operations around. And I'm happy to announce that since last month, we are present in South America, as well, with offices in Chile and Peru. Briefly about the services, so what we provide is basically ranging from standard exploration, drilling services, technical drilling services, also production drilling, as well as some other services such as designing of the drilling program, providing geological and geophysical and hydrological tests and surveys, as well as providing some specific reports and interpretations of the work. Basically, we can sum up all these mentioned and not mentioned services under one package and act as a one-stop shop company in a way that GEOPS provides full service at a single project. A good example here, we have the project in Asar al-Medet mine here in Bulgaria, where we managed to respond in a way to facilitate all required services ranging from project designing and supplying materials, equipment, then also providing geological and hydrological and geophysical work with the report at the end of all the work that's been done. And of course, we did the drilling as well. So these are a few more photos from the site. GEOPS as a company is also quite known in the mining society, so to say, for its speed adaptation to some specific project requirements by relying on its manufacturing facilities and extremely creative stuff. As an example, here we have the Velocity project in Rozino near Krumovgrad, again here in Bulgaria, which was challenging in a way that we had to actually develop tools, specifically the portable drill rig, that would be suitable for the terrain, the specific as it was there in this place. Ultimately, we managed to manufacture the rig that responded very well in few terms. First of all, given the rigid terrain, it responded very well. We got very good results, and by that, it enabled us to minimize the costs by simply minimizing the infrastructure spendings. And ultimately, what is interesting about this kind of equipment is that it suits and responds very well in areas that are subject to some specific environmental restrictions, such as Natura 2000. Then another type of drilling that I want to mention today is directional multilateral drilling of wells going up to 1,500 meters. So this particular case, as you can see on the graph, is the project for exploration of multi-ore body that we did for El Dorado in Serbia. It was back in 2017 when the company has successfully completed the project in a way that in total it was 27,400 meters of directional drilling. That included also multilateral holes, each with 4 daughter boreholes at total length of 7,800, as you can see. So it's done in a way that all these daughter holes are using actually one mother hole to about 400 meters, after which the deviation begins within 100 meters to reach the desired trajectory. And with the HQ motor, we reach a 6-degree adjustment every 30 meters, while the largest correction of the inclination in this particular project was actually 32 degrees. Ultimately, in the end, we managed to reach the deepest borehole at a depth of 1,200 meters with NQ diameter of the core. It's not working. There's maybe not. Yeah. Okay. Here's another case of directional drilling with a maximum length of 2,200 meters, at which we managed to maintain the same trajectory with a maximum deviation of 5 meters in radius. This project was again in Serbia for a client there in Timok region, and the bore plan has included 2 targets in the ore zone that had to be intersected. During the drilling process, the bore trajectories were continuously monitored and where necessary corrected. The return to the main stem in the right direction that included the planning, the approval of the plan, the punctuality and other activities could be done in one shift. At these depths and with an accuracy requirement of 5 meters in radius, as I said, the maximum allowed deviation is 1 degree from the planned trajectory. In the end, deviations are made with HQ downhole motors. Now this graph shows us the process of directional drilling with one stem that was done by our company in 2017. And the goal was actually to determine the presence of hot water. In both cases, boreholes were vertical in the first 250 to 300 meters, after which the targeting begins. We used NQ downhole motor as well as mechanical navy tool, ultimately achieving a result of 9-degree correction within 30 meters. In this particular case, the correction of the inclination is 14 degrees, ranging from 90 to minus 76 degrees. The borehole here is 800 meters deep, where it passes 9.2 meters away from the predetermined point. And lastly, here's an example of the directional drilling we have conducted for the purpose of reaching the underground gallery target. And it was done here in Chalopech in Bulgaria, and it was actually for the construction of exploitation drilling wells for backward passing. Of course, I mentioned underground drilling. We had a number of, and still ongoing, a number of such projects. Just to make mention, it's the project here with Dundee Precious Metals, ongoing project in the mine Sasa in North Macedonia, mine Grot in Serbia, and others. Now, as I said, the concept of one-stop shop company providing full services by single company. Here is another example. It's from Poland, where again, our company provided full services, but the main characteristic of this project is that it was done in a conditions of abnormally high gas pressure. So very specific circumstances. But the project was about the drilling of the core prospection boreholes in order to determine the setting of copper-bearing horizons. Again, our company has provided full services, I said, starting from designing the project, constructing the infrastructure, of course, drilling, doing the geophysical surveys, and ultimately doing the recultivation, so bringing back the area into its first condition. This is actually one structure of the borehole we had there, and the depth we reached at this particular one, was 2,000 meters. Now, probably the most interesting part, and for us definitely the most challenging one, was the project we did for Rio Tinto in the Jadar project in Loznica in Serbia. It's for lithium drilling. It was challenging in a way that the client requested from us to deploy extremely large diameter, for which we used Atlas Copco's RD20 rig with 50-ton pullback capacity. But besides the rig, all other equipment couldn't be found on the market. So the company had to develop its all other necessary tools and equipment on its own. And finally, we produced something that was a triple tube conventional core barrel with an outer diameter of 444 millimeters that can collect 3 meters of 292 millimeters diameter core. So something unusual. In kilos, if you just look at this, it's like when empty, 1,500 kilos weighing, while when it's full, 1,800 kilos. A special drill bit also had to be designed with the diamond inserts for this job, and ultimately we have managed to extract 40 tons of material for technological and metallurgical tests and reach the depth of 623 meters. And yeah, more important to mention is that this job particularly was done completely in accordance with the standards of safety of Rio Tinto and with zero incidents, for which we are extremely satisfied. Ultimately, just to recap, these are some of the companies we were cooperating and still work with. Over the years, we built a strong network of clients and a very strong relationship that enabled us actually to reach the point where we are today. And it's the philosophy that we are going to rely on in the future. We are focused and happy to speak to everyone in expanding to new markets, and hopefully we will be able to provide our services to some of you, and you would be able to confirm by yourself to all what we said today, what the company provides. So thank you once again. And
thanks very much, Najaz. A very useful insight into the capabilities of GEOPS. And obviously, any questions, please approach Najaz after the break. Yeah, or there's also a table in the foyer that you can approach the guys there. Okay, so next up is Todd from who's a director at Olympus.
Thank you. Well done. Good afternoon, everyone. Thanks for having us here this year. This again is another fantastic conference, and I hope everyone's enjoying the quality of the presentations. I think this has been a great session because of all the case studies that we've been presenting today. And I'm going to continue in the same vein and introduce some real-world examples of the use of portable XRF in this region. As Alex suggested earlier, portable XRF is not a new technology, but our customers continue to use the technology in really new and interesting ways, as Alex has demonstrated he's done with his company. So I'm going to show you some of the innovative ways that some of our customers have been using this technology in this region. So I'm going to introduce Olympus, but then talk about projects undertaken by Tethian Resources in Serbia, Eldorado Gold in Greece, Minico in Bosnia, and Ariana Resources in Turkey, if I have enough time. Thank you very much to all those companies for sharing your stories with Olympus and you guys. So, for those that are slightly confused, yes, Olympus is the Japanese manufacturer of cameras, but we have a huge industrial division that works across all sorts of technologies, not only cameras, consumer cameras, but perhaps the most interesting thing about Olympus this year is that Olympus is celebrating its 100th year. In 1919, Olympus produced its first microscope, from which it's well known in the geological community. So it's 100 years this year that Olympus has been a company. Headquarters are based in Japan, but the analytical instrument division, which I work for, in the minerals space, it looks after portable XRF and also portable XRD. So back to Physics 101, portable XRF produces chemistry. We have some equipment at our booth if you would like to see it. We direct the instrument at a sample, and within a few seconds the instrument will tell you the chemistry of that sample. Now, there's a lot of variables as to the accuracy, precision, the length of test time, homogeneity of the sample, matrix. There's a lot going on, but results can come, reliable results can come in as little as 10 to 30 seconds. You get the elemental concentration for 30 plus elements on the screen of the instrument. With respect to that's X-ray fluorescence, portable XRF. With respect to our portable XRD, XRD stands for X-ray diffraction, a well-known analytical technique that has been confined to the laboratories for the last 50 years, but recently NASA developed this technology to go to Mars and study the mineralogy on Mars, on the Pathfinder. And so the technology that's in the Mars Pathfinder is used in our portable XRD. It has some unique analytical capabilities that are not associated with a traditional goniometer, but using sonic resonance to rotate the sample rather than the detector and the tube, so that we can have the detector and the tube in a fixed position. The portable XRD's got a lot of applications in the mining side of the business to study the ore bodies and the mineralogy of particular ore bodies to ensure that good grade material without penalty minerals is going to the mill. So the first case study, I'd like any further information on the technology, please come and see me this afternoon or this evening. The first case study is the Tethyan Resources project. Tethyan Resources are exploring for zinc and lead vein mineralisation and copper, gold porphyries in Serbia. This project has a special place in my heart because this work was conducted, this work's very recent, the Rudnica project, but I was on this project 15 years ago with Freeport when they were looking at the project. So it's funny how projects come around through their cycle. So what you can see here are the results of portable XRF and ICP-MS analysis on soil samples collected on the lead-zinc vein mineralisation project. What Tethyan are doing is collecting the soils, sieving them to 2 millimetres and testing them directly through the calico bags. So the results are not exactly the same as the laboratory. Of course, we're doing very little sample preparation. We're testing through a calico bag, but it's cost effective at an early stage of exploration. It doesn't require them to send hundreds of samples to the lab, and they're making rapid decisions in real time. So it allows them to design and implement a follow-up program for their soil survey immediately. Now, there's not a lot that's innovative about this. This is routine, really, all around the world in a large number of exploration companies. This is an example of one particular project at Rudnica on the copper-gold porphyry, where you've got the laboratory. So this was a historic lead-zinc vein targets which had limited drilling for the copper gold in the mid-2000s, as I referred to. And so Tethian conducted the first pass portable XRF survey, which you can see in map A, where they did a few samples and they identified a moly anomaly. The red dots are between 10 and 30 parts per million moly in soil. So they then did a follow-up soil testing program with ICP and confirmed the anomaly based on the laboratory results. And so mapping and later drilling confirmed the presence at these two projects. The more innovative stuff that Tethian's doing is the work on their drill core. So Tethian are testing every 30 centimetres on uncut drill core and preparing reports on a daily basis to their directors to identify the copper, moly, lead, zinc as indicative results, first pass, and also differentiating their intrusive rocks from their basement. You can see the different, on the bottom right, you can see that it's assisting the geologists to log and map the different basement ophiolite rocks from the younger igneous rocks, which are, I think it's chrome and nickel is the differentiator. Chrome and nickel are the differentiator on the rock type work. And this seems to be the direction in which portable XRF application is going in identifying rock types. Not just looking at pathfinder elements or base metals, but using more thorough lithogeochemistry to identify rock types and help understand your deposits much better. So the second project, second case study is El Dorado in Greece. It's obviously primarily a gold company, but portable XRF and TerraSpec for mineralogy have been used to extract new information about the deposit, as the historic coarse rejects and pulps were previously only analysed for copper and gold. So the project was all about trying to understand the deposit better with more thorough geochemistry. So the workflow or procedure that was followed for this project was cataloguing all the old historic pulps and coarse rejects, sorting them, cataloguing them, and then making a perfectly prepared sample using a press to make a sort of hockey puck type sample, which has a consistent density, is very fine grained using the pulps. So it's the ideal sample for portable XRF to replicate, to try and get the best possible data, particularly on the light elements, which is more greatly impacted by density and particle size. So they were using the reflex pellet press to produce a really homogeneous sample, and then this is the workstation, a portable XRF in a workstation run by a laptop computer, and then this data is uploaded into a cloud-based data management software system, which is run by Reflex, which is part of the Index group. Reflex are actually Olympus's largest portable XRF customer, with around 40 analysers that they rent around the world, and also offer additional services. They have a software system that runs the XRF with a built-in QA/QC module where you can insert standards, blanks. They have sample preparation equipment, a crusher, a mill, the press, and then they have this data management system which manages the portable XRF data, and then you can send it into their geochemistry management statistical software, which is IOGAS. Some of you may or may not be familiar with IOGAS. And what IOGAS can do is produce beautiful logs of these drill holes to understand your deposit better using multi-element geochemistry that was not obtained from previous laboratory assaying. From IOGAS, you can output that data directly into Leapfrog, so you can start visualising your portable XRF data immediately once you've taken that test at the end of the day, for example. It's becoming a really common theme to integrate your portable XRF data into your software systems, whether it's Maxwell, whether it's Micromine, whether it's Leapfrog, Datamine. That's one of the things that we're really working on, to integrate our data into the systems that you're using. And portable XRF case study, and Tim Baker is the chief geoscientist that was doing this project, if you're interested in more information. He's based in Vancouver. So portable XRF case study number 3 is MINEX in Bosnia and Herzegovina. It's the lead cerussite project at Olivo. This is a narrow vein cerussite project, which has variable deposit size, geometry, alteration and mineralisation style. It's a complex project. It's mostly high grade at above 30% in very narrow structures. Exploration phase lasted until 2017. Underground mine development happened between 2016 and 2019, and processing construction's going forward next year. Last 2 slides. So they needed something low cost, something simple, something rugged, but highly accurate, that could handle high sample throughput, was repeatable, and had good manufacturer support. So they chose to work with us. The Vanta instrument you see out there is being used by at the Olivo mine as the principal analytical tool. So up to 50 samples per shift. That mine site is doing a lot of other work for the MINEX deposits, nearby deposits and other mines, and it's been incorporated into the metallurgical process. So the main application is quick turnaround decisions from mining operations, especially in stockpiling and blending, and it was crucial in their view during the exploration phase, and it is the core piece of equipment running their laboratory. So that is pretty innovative in itself. And it's used around the clock and used in a workstation in similar mode that you saw the Eldorado. We've got a lot of other XRF case studies. It's something we work on. Elacetar, gold concentrates. The instrument can measure waste, tailings, environmental samples. So it's not only exploration phase or mining phase, it's right through from scrap metal right through to tailings. So from exploration, right, we cover the whole mining life cycle with this technology. Thanks very much.
Thanks very much, Todd. Some very interesting case studies there on innovative XRF handheld use. So we've got our final presentation now by Marcin Loska, who's the chairman of the board at the Proxys company.
Good afternoon, ladies and gentlemen. My name is Marcin Loska, and I'm a chairman of the board of Proxys company from Poland. And I have a pleasure to present you some information about Smart Exploration project. MINEX Forum was very interested in idea of the project and its results. There was some article published also a few months ago about our activities in Portugal and Kosovo. So that's why we have been invited to this event, and on behalf of executive board of the project, I would like to thank for having us here. Few words about the main objective of the project. The main objective is just to develop the new innovative tools and methods for geophysical exploration which would be cost effective and environmentally friendly, which means non-invasive. And that would help us increase awareness and acceptance, social acceptance of exploration activities, and at the same time increase environmental issues and return time. As you can see, Smart Exploration is a consortium consists of 27 partners from 9 EU countries. The consortium includes 11 SMEs and what is interesting, one civil society organization, it's Ludwika Kommune. Smart Exploration partners are divided into 3 groups: research, innovation and action. Research group consists of mainly universities and research institutes, while innovation is represented by mainly SMEs and companies that they provide new innovative solutions. And action group is represented by mining and exploration companies. This project is, the leader of the project is Uppsala University. It started in December 2017, that its duration is 3 years, so we are just halfway. And there are some very positive results of the outcomes of the project. What are these new tools, innovative tools that we develop under the project? The first one is eVibe. It is developed by Seismic Mechatronics together in cooperation with TU Delft. And this is the device that vibrates the ground in order to map the subsurface by using echoes to create visuals. It is in a similar manner to ultrasound technology. This prototype is environmentally friendly. It's all about electronics. There's no pollution at all. It's portable. It can be used underground in the tunnels. And actually, it has been already tested in seismic site in Netherlands and also in Portugal, Nevskovo mine. The next instrument is UAV system. It's georeferenced UAV, the broadband EM data acquisition system, and in parallel there is a ground-based frequency domain electromagnetic system that can measure the EM signal to the depth of 1.5 kilometers. This system is ready to be tested, and it will be tested in Sweden this year. Then the next one is GPS time transmitter system. And thanks to that system, you can acquire simultaneously in a synchronized time the seismic data from the tunnel and from the surface. And this system has been already tested in Portugal, Nevskovo mine. This system has been already filed for a Swedish patent, and it's ready for market development commercialization. The next tool is, or method, is a SkyTem system. It's helicopter-based deep penetrating probing with TEM, and it's advanced to the existing technologies. Is that there's this transmitter signal is increased, therefore there's the deeper investigation, and of course there's the level of the noise is reduced. These are main advantages. And SkyTem already tested its system at own premises, and it will be tested soon, I think in 1 or 2 weeks' time in Sweden. The last one is a slim hole system. It's a modular-based borehole data acquisition system. And it uses hydrophones that communicate with the surface through Ethernet cables. And it can be used for acquisition data of boreholes at the depths of 1.2 to 2.2 kilometers. By using the hydrophone sensors, it creates a much faster, significantly faster acquisition of data than a geophone-based system. Now, about the short information about the sites that are tested within the project. The thing is that among 6 work packages within the project, there are 2 the most important ones. One is work package number 4, which is target generation, and there's the second one, work package number 5, which is validation. So in the first work package, we just gather and process or reprocess the historical data, and then we perform a standard geophysics survey in order to generate the target, which would be then validated by new tools and methods in the next work package. So there are 6 sites, 2 in Greece, and then Kosovo, Portugal, Sweden, Finland. Just a short description. The first one is Gerolikas bauxite exploration site owned by the Delphi de Stomon. This is the estimated resources is at 100 million tons. The second one is Hellas gold exploration site, and our project focuses on project called SCORIS. So it will be validated by Skyton. Then we have Neves Corvo mine in Portugal with its deposits of copper and zinc. This task has already been done with the eVibe. The tests are really, really positive, and I think we will be able to represent the results very soon, maybe at the end of the year. Then we have Blöteberg mine site in Sweden, which is owned by Nordic Iron Ore, and there is a iron oxide deposits. And this site will be really, really tested because there will be UAV systems, Skyton system, and slim hole system validated. The next one is Silinjärvi mine in Finland. This is the biggest open pit mine in Finland, and the biggest EU phosphate mine, or the only phosphate mine in production. I think that as far as I remember, the UAV system will be used there for validation. And then there is the Kosovo chromite exploration sites. It's Bodyford time chromite. As you can see, there are 2 licensed areas. One is very close to the border with Albania, and the other one is very close to the border with North Macedonia. We have been invited as a company to this project because of 3 reasons. The first reason was that the chromium is one of the 27 critical raw materials enlisted by European Union. The second reason was providing access to greenfield, we created a balance to other locations which are mines. And the third reason was that we are an SME, and the European Union highly appreciates involvement of SMEs in Horizon 2020 projects. I would like to say a few words about my company. We are a small consulting company which provides services in mining, exploration and metallurgical industry. What we can do is mineral deposits recognition and exploration, and also management of exploration projects executed in Europe, mainly Western Balkans. That's where we have our established contacts, and Africa. You can see the commodities we are interested in. I can only add that there's also a quartzite that's missing. We are very closely cooperate with the only ferroalloys producer in Poland, and also the only tin smelting facility in Rwanda. And recently we have been awarded a contract for exploration of 8 licenses for cassiterite in Rwanda. Our role in the project was to provide an access to chromites licensed areas for the purposes of service. There were 2 parts of service done already under work package number 4, target generation. They were performed by another smart exploration partner from Poland. It's a company called GeoPartner from Krakow. And we have a representative of GeoPartner here in person of Marta Bernard. So the first part, magnetic and gravity measurements, were done last year in April, and then electric resistivity tomography and induced polarization were performed this year in May. So now all the data have been gathered, and they are being processed in order to create 3D models. And upon the results, there will be a validation, hopefully this year in October by Skyton. Thank you for your attention. That's it from my side. I would like to introduce Martin van Schaik from EAG, also a partner of Smart Exploration. Please continue presentation. Thank you.
You will not know. Let me see. So for those unfamiliar with EAGE, we're one of the largest geoscience associations, rather multidisciplinary. A good section of it is to do with our, what we call the Near Surface Geoscience Division. And our Geoscience Division basically consists of a lot of people working within the mining industry. So a lot of the partners of this project are also members, individual members of EAGE. We've got activities all over the globe, and we've actually been facilitated with a number of offices. I myself am based in the Netherlands, but we also have offices in Kuala Lumpur, Moscow, and Bogota, as well as Dubai, to facilitate that membership and to really get the message about the scientific research that we work on out to our members. So if it comes to EAGE and knowledge dissemination, there's a number of things how we actually try to do this. We are very much into community building and creating visibility. So we do not necessarily just present at these kind of conferences, but there's other ways of trying to get involved with these projects. The central platform for our Smart Exploration project will be the smartexploration.eu website. But one of the things that we wanted to stipulate here is really to have a really broad spectrum on social visibility, of media visibility as well. So the team has actually decided to really help our partners in the Smart Exploration to create all sorts of videos, give young professionals, for instance, a platform as well to talk about their research. So instead of just looking at a presentation or an article published in a journal, we really wanted to give people a bit of a platform to really put a name to the various elements of the program. So these would be, for instance, the rapid fire talks, 2 to 3 minute presentations from young professionals, quite often PhD students, but also young researchers, to really talk about their engagement with the project. Last but not least, I mean, we do try to increase the visibility to audiences such as yourself, as well at events, of course. For instance, PDAC, we had a stand there and a couple of presentations from our partners. But in addition, I mean, obviously, based at MINEX, EAGE conferences, such as the annual conference that we organized in July, but also the near-surface conferences in September are great platforms for that. The next place you will be able to find us will be Saga in October. So yeah, looking forward to seeing you there.